There is an event in the universe so violent that a single occurrence, aimed at Earth from across the galaxy, could begin the collapse of most complex life on this planet within seconds. Not minutes, not hours, seconds, before any alarm could sound, before any shelter could be reached, before any government could issue any warning, before anyone on the hemisphere facing the burst could do anything at all except live through the first moment of a catastrophe that had already arrived. The event is called a gamma-ray burst. It belongs to the most energetic explosions known in the universe. In a few seconds, a gamma-ray burst can release more energy than our sun will emit across its entire 10 billion-year lifetime. In the most extreme cases, if you describe the beam as though its energy had been radiated equally in every direction, the equivalent energy becomes almost impossible to hold in your head. All of it released in seconds. All of it focused into a beam. All of it traveling at the speed of light. And if that beam were pointed at Earth from within a few thousand light years, a small fraction of our galaxy's diameter, what follows is not a natural disaster in any conventional sense of the word. It is not an earthquake, not a storm, not an impact crater. It is the atmosphere itself being chemically rewritten above our heads. Let's follow the timeline. First, understand what a gamma-ray burst actually is. There are two main types. Long gamma-ray bursts, lasting more than 2 seconds, sometimes minutes, are produced by the collapse of massive stars. When a star more than roughly 20 times the mass of our Sun exhausts its nuclear fuel and its core collapses into a neutron star or black hole, the collapse can produce 2 jets of gamma radiation and relativistic plasma, firing outward from the poles of the collapsing star at nearly the speed of light. The jet punches through the outer layers of the dying star and extends outward into space, radiating with a luminosity that briefly outshines the combined light output of the entire observable universe. Short gamma-ray bursts, lasting less than 2 seconds, are produced by the merger of 2 compact objects, typically 2 neutron stars or a neutron star and a black hole. The merger, as LIGO has now confirmed in the gravitational wave event GW170817, produces a cataclysmic release of energy including a gamma-ray burst, the electromagnetic counterpart to the gravitational wave signal. Both types can produce the same terrifying product, a focused beam of gamma radiation traveling through space at the speed of light, carrying in seconds an energy output that, in the brightest events, exceeds what a sun-like star will radiate over its lifetime. If that beam intersects Earth, the sequence of events begins at the moment the first photon arrives. 0 seconds. The gamma radiation arrives at the speed of light. There is no warning. Gamma rays travel at the same speed as the light from the burst. Any optical brightening arrives at the same moment as the lethal radiation, not before it. There is no electromagnetic precursor that travels faster. There is no practical early warning system for a direct hit. On the side of Earth facing the burst, whichever half of the planet happens to be turned toward that point in the sky, the gamma radiation enters the upper atmosphere. Gamma rays are the highest energy form of electromagnetic radiation. If there were no atmosphere above us, they would be lethal in the most direct possible way, ionizing molecules, breaking chemical bonds, damaging DNA, disrupting the machinery of cells. But Earth has an atmosphere. The gamma rays do not meaningfully reach the surface. The atmosphere absorbs them. This absorption is the beginning of the catastrophe, not the end of it. When gamma rays are absorbed by atmospheric molecules, the energy does not simply disappear. It is converted. The gamma rays ionize the nitrogen and oxygen of the upper atmosphere, stripping electrons, creating a plasma of charged particles, driving photochemical reactions that normally occur only at minimal rates. One of those reactions is the destruction of ozone. Ozone, the molecule O3, comprising 3 oxygen atoms, forms a layer in the stratosphere approximately 15 to 35 kilometers above Earth's surface. It absorbs ultraviolet radiation from the sun, preventing the most lethal wavelengths from reaching the surface. The ozone layer is what makes the surface of Earth habitable for life with exposed DNA, which is to say, essentially all multicellular life. A gamma-ray burst striking Earth's atmosphere would destroy a significant fraction of the ozone layer. Not gradually, not over months. In the seconds to minutes of the burst itself and the hours and days following, as the nitrogen oxides produced by the atmospheric ionization spread through the stratosphere and catalytically destroy ozone molecules. Atmospheric models suggest that a gamma-ray burst from within a few thousand light-years, a relatively nearby source by galactic standards, could remove a large fraction of the ozone layer. One well-known model found globally average depletion of roughly a third, with some regions losing more than half. Other scenarios can be worse depending on the burst's energy, distance, latitude, and season. The burst itself lasts seconds. The ozone destruction would persist for years. 30 seconds. The gamma-ray burst is ending. The most intense radiation has passed. The initial energy deposition in the atmosphere is complete. On the surface, there is no instant wall of fire. No global flash that burns continents clean. The acute effects at ground level, the direct killing of organisms by the gamma rays themselves, are limited by atmospheric absorption. The atmosphere is a shield, and it held. What it had to do in order to hold the shield is the problem. The ionization of the atmosphere produced nitrogen oxides, NO and NO2, in quantities vast enough to matter globally. These nitrogen oxides are chemically active. They attack ozone. And ozone, once destroyed, recovers slowly, over years, as solar ultraviolet radiation slowly reforms it from ordinary oxygen. In the meantime, the sun, which was always radiating ultraviolet light, always would have destroyed life on the surface if not for the ozone layer, continues to shine, with nothing stopping it. 1 hour. The burst is over. The sky looks approximately normal to anyone surviving. The ozone layer is already damaged. Modeling the exact timescale depends on the burst's energy and distance. For a moderate event at a few thousand light years, significant ozone destruction would be detectable within hours, becoming catastrophic within days as the nitrogen oxide spread. On the surface, nothing seems immediately wrong. The temperature has not changed. The air is still breathable. The sun still appears in the sky. But the ultraviolet flux reaching the surface has begun to increase. Not yet dramatically. Not yet in a way that would be obvious to casual observation. But measurably, in the instruments of any observatory monitoring solar UV output at the surface. One day, the UV flux at the surface has increased substantially. For organisms without UV protection, without melanin, without shells, without the ability to retreat to shade or depth, exposure to the dayside sunlight is becoming dangerous. Phytoplankton, the microscopic photosynthetic organisms that form the base of marine food webs and produce approximately half of Earth's oxygen, are among the most UV-sensitive organisms. They live in the sunlit surface layer of the ocean, where they require visible light to photosynthesize but are normally protected from lethal UV by the ozone layer. Without that protection, phytoplankton exposed to direct sunlight begin taking damage. Not all at once. Some species are more resistant than others. Some patches of ocean are less exposed than others, and water itself provides some shielding. But across the sunlit ocean surface, the productivity of the organisms that sustain every marine food chain begins declining. On land, the effects are initially less dramatic. Most land plants have some UV protection, waxy coatings, reflective surfaces, DNA repair mechanisms. But even these protections fail under sustained elevated UV flux. The agricultural implications are severe. Most crop plants are not adapted to the ultraviolet levels that would prevail after major ozone depletion. Crop failures across the sunlit surface would begin within days to weeks of the burst. 1 week. Ultraviolet radiation levels at the surface are now multiple times their normal value during daylight hours. Being outside in direct sunlight is dangerous for any organism without adequate UV protection. Human skin, in normal sunlight, can tolerate approximately 15 minutes before sunburn. Under post-burst UV conditions, sunburn would occur in a fraction of that time. Human civilization can adapt. We can cover our skin. We can limit outdoor exposure. We can move food production to artificial lighting. We are not, in the immediate weeks after a nearby gamma-ray burst, facing extinction. We are facing the beginning of a collapse in the systems that feed us. 1 month. The ozone continues to be depleted. The nitrogen oxides persist in the stratosphere longer than the initial burst. They are being continuously refreshed by ongoing photochemical reactions driven by the elevated UV flux, and they spread globally, affecting even the hemisphere that was not facing the burst during the initial event. Marine food chains are disrupted. Phytoplankton populations have declined across much of the sunlit ocean. The organisms that feed on phytoplankton, zooplankton, small fish, the entire bottom of the marine food web, have less food. The collapse propagates upward. Coral reefs, already bleaching under UV stress, are dying more rapidly. Agricultural output is declining across regions exposed to elevated UV. Governments are rationing food. Supply chains built on the assumption of normal solar conditions are failing. The global food system was not designed for sustained post-burst UV conditions. Nothing about modern civilization was. 1 year. The ozone layer is partially recovering in some regions. The nitrogen oxides are slowly being removed by natural atmospheric processes. But the damage is not repaired. Recovery takes years, potentially decades, and during the recovery period the UV conditions at the surface remain elevated. Marine ecosystem disruption has propagated through food webs that took millions of years to build. The recovery of phytoplankton populations does not automatically restore the fish populations that depended on them. Ecosystems rebuild slowly, if they rebuild at all. On land, agriculture in the most affected regions has been severely disrupted. Famine conditions exist across significant portions of the world. The gamma-ray burst itself lasted seconds. Its effects are still being felt a year later. Here is the specific question that the paleontological record raises. The end Ordovician mass extinction, approximately 445 million years ago, killed approximately 85% of marine species. It is the second largest mass extinction in Earth's history, exceeded only by the end Permian event. The cause has been debated for decades. The timing coincides with a rapid glaciation of the supercontinent Gondwana. Ice ages are typically associated with mass extinctions due to sea level drop and habitat destruction. But some paleontologists have argued that the pattern of extinction, specifically the preferential loss of shallow water marine organisms that would be most exposed to UV radiation, is consistent with a gamma-ray burst. The evidence for this is indirect. Gamma-ray bursts leave no geological signature. A burst that destroyed the ozone layer would not deposit a chemical layer in sediment the way the Chicxulub impactor deposited iridium-enriched material. There would be no crater, no anomalous element concentration, no physical record distinguishable from a natural extinction driven by other causes. A gamma-ray burst could have caused the end Ordovician mass extinction, and we would not be able to confirm it. This is not a definitive claim. The glaciation hypothesis is well supported. The evidence for the gamma-ray burst hypothesis is circumstantial, but the circumstantial evidence is consistent, and the possibility has not been ruled out. If it happened once, it happened. If it happened once, it could happen again. The probability of a gamma-ray burst from within a few thousand light-years, aimed at Earth, occurring in any given year is extremely small. Gamma-ray bursts are rare events in any individual galaxy. The beaming of the jet means that only a small fraction of bursts would be aimed at Earth, even from a source within the Milky Way. The combined probability of a burst occurring close enough to affect Earth and aimed precisely at our planet in any given human lifetime is extremely small. This is not an imminent threat, but the universe is very old. The Milky Way has existed for over 10 billion years. In that time, the probability of a burst occurring at the right distance and orientation to affect Earth at some point is not negligible. The end Ordovician extinction, if caused by a gamma-ray burst, would be evidence that this probability, while small per year, is non-zero per billion years. The galaxy does not care about our timescales. It operates on its own. In 2022, the brightest gamma-ray burst ever recorded arrived at Earth. Designated GRB 221009A and nicknamed the Boat, brightest of all time. It originated approximately 2.5 billion light-years away and was so intense that it saturated the detectors of multiple space telescopes simultaneously. Instruments designed to measure powerful gamma-ray events were overwhelmed by its intensity. Despite originating billions of light-years away, so distant that the photons had crossed intergalactic space for a significant fraction of Earth's history, it was the most intense gamma-ray burst ever observed at Earth. At roughly 2 billion light-years, the event was far too distant to threaten life on Earth. Our atmosphere absorbed the burst without biological consequence. No ozone catastrophe followed. No animals were harmed. But Boat illustrated something important about the scale of what gamma-ray bursts can do. An event so powerful that it overwhelmed instruments designed to study the most energetic phenomena in the universe from billions of light-years away, produced only a faint atmospheric whisper at Earth. If Boat had originated from within our galaxy, from within a few thousand light-years, the echo would not have been faint. The sun will rise tomorrow. The ozone layer will be intact. The ultraviolet flux at Earth's surface will be what it has been for the past several hundred million years, high enough to cause sunburn, but low enough for life to thrive on the land and in the surface ocean. This is the normal condition. This is what every organism alive today has evolved within. The gamma-ray burst is the condition that no organism currently alive has ever experienced. The event that damages the protection, that turns the sun, the source of almost all usable energy for life on this planet, from a nurturing presence into a direct threat that begins in seconds, before any warning, before any response, by disrupting in the upper atmosphere what life has relied on for hundreds of millions of years. It is a small probability per year. It is a real probability per billion years. The universe has been doing this for billions of years, in galaxies throughout the observable cosmos, producing events that reshape the biological histories of any worlds unfortunate enough to be in the path. Whether any of those worlds had observers, whether any intelligence was present to watch the sky change and understand what was happening, we do not know. What we know is the physics. And the physics says that on a day indistinguishable from any other, from any direction in the sky, at any moment, the universe is capable of deciding to change the rules. Without warning, without cause, without any regard for what has spent 4 billion years building itself in the path of the beam.